Hello everyone, I'm Juni. This is the second week lecture for supervised learning. In this week, we will mainly go over various machine learning methods, especially for regression problems. So in this week, I will explain more about the basic concepts of regression problems. And throughout this week lecture, I hope you have the better understanding for the concepts of the various regression methods like local regression, polynomial regression, regression with step functions, and spline. I also want you to have a good understanding for principal component regression and partial least square. And finally, we will have a chance to practice the various regression models with R. First, regression problem itself. A regression problem is finding a function between x and y, especially y for a continuous outcome variable y. Y can be a height, salary, exam score, or rainfall, or so many continuous values. In the last week, we already have discussed about linear regression. Linear regression is a typical method for these regression problems. However, linear regressions are too simple and it is strictly limited. The major limitations of linear regression is, first, it cannot capture non-linearity, non-linear relations. And the second major limitation is that linear regression doesn't have the good way to apply for high-dimensional data with many input variables. To overcome such limitations, especially to ensure non-linearity, some other methods like Lewis or spline, these are developed. And to consider the high-dimensional data, principal component regression, or in short PCR, or partial least square method, in short PLS, they were introduced. In this week, we will go over these advanced methods for regression problems. Okay, so first, local regression, or Lewis. So Lewis actually comes from LONESS here. So it's Lewis. Let's consider a simple case with one x and y, capital Y. Here is the horizontal axis is for x and the vertical axis is for y. If the data point looks like this, these are the data point. There is actually no way to apply an ordinary linear regression because this is definitely not linear. Okay? The data is not linear at all. Then how can you find out the function f which explains y with x to capture such non-linearity? The idea of Lewis is applying an ordinary linear regression with only local samples. For example, if we want to find our function around this point, so we want to find out this function of, let's say this point is x, the x of the x, something like that at this point. We find an ordinary linear regression line with only samples around this point. That means we want to find out this linear line because we only consider those the nearby points. Okay. If we want to find f, let's say another point, let's say this point, here this point, we may want to use another set of sample like this, then eventually we may find out another linear line like this. Okay. So actually, every single point like this point, or this, every single point gonna use a different line, and the overall line becomes totally smooth line that goes through the given data set. Because the actual this line, okay, so again this line is only applied to this line, even though it's a next. If we want to estimate point in the next point, it may use this set of samples, so it is more like this kind of line. So because all points are continuous, the final fitted line will be very smooth line like this. Okay, so let's erase it, then let's draw it, something like this. Okay, it's gonna be the final line. So when we find a linear line around the certain point, only its neighbor data points are considered. But however, it does not necessarily mean that the only neighbor points are considered and the other points are not considered at all. It doesn't mean that situation. Actually, all data points are considered. We consider all of these data points, however, with different weights. If a data point is close to the point of the estimation, it is considered with high weight. Okay? If data point is far away from this estimation point, then it's gonna have the very small weight, almost zero weight. Usually, people like to use the bell-shaped curve or normal distribution curve for this way, something like this. Okay, so if it's close to the estimation of point, it has the high weight, large weight. If it's far from, it has the very low weight, according to this line. Okay, so mathematically, this one can be expressed in this way. The RSS of the ordinary linear regression is given like this, as you've seen from the previous lectures. The RSS of the law is given as weighted sum of this error, Wi. This weight Wi is often defined as the normal distribution form, something like this. So if we rewrite this one, this is e to the minus xi minus x square of 2 tau square. So this is exactly very similar equation for the PDF of a normal distribution. Here, this tau is the variance of the normal distribution, and it determines the width of this curve. So if this tau is very high, so if we have the large variance, this curve gonna like this. Then we have the wider width. Then we gonna include the more data set, more data point. However, if this tau is small, we gonna have the narrow curve like this. Then we gonna include the less data point. Extremely, if tau is very large, the Lewis will consider all data points and almost equally, then it becomes similar to the ordinary linear regression. Here you can see that the flexibility of Lewis is controlled by this tau. Okay? Large tau makes the lines at all x points are similar to each other. So it is reduced flexibility. Instead, low tau makes the whole line is very wiggly. So it increases the flexibility. Okay. This normal distribution is not the only function for weighting. We can simply use a rectangular function, which consider rectangular function like this. which consider values within the range equally, but it doesn't consider the data points out of this, the outside ones at all. Similarly, in this case, the flexibility of the LOIS can be controlled by width of these, the rectangles. Compared to the ordinary linear regression, the local regression is very non-parametric. Even though it locally uses a linear model, overall it doesn't assume anything, while the ordinary linear regression assumes a very strong linearity over all ranges. And definitely, LOIS is much more flexible, and the flexibility is controlled by window size. Since LOIS finds different lines at different points, usually it requires more computational power. Since it uses only a subset of the data point, to have a similar estimation, in order to have a similar estimation power with an ordinary linear regression, it often requires more data point. Since LOIS focuses on a few and the local data point, it is also easy to be distorted by outliers. Okay. Then next is polynomial regression. We already have seen this polynomial regression with the higher order terms in the previous lectures. The disorder linear regression is a linear regression with x and x squared, x third, up to x to the d's. In total, this model has d variables. This figure is from the previous slides, lectures of the previous slides. This dot, each dots are the observed data, and the blue line, this blue line is for the second order polynomial regression, which is y is modeled by beta 0 plus beta 1 x plus beta 2 x squared. And this is the cyan one, wiggly one. This one is from the fifth order polynomial regression. This is up to x fifths. As you see here, a model with the higher order term is more wiggly and more flexible. However, it is not always good, as you see here. Okay? Compared to the ordinary linear regression, polynomial regression is still parametric, as you see from its equations. And it is more flexible because it included more terms, and the flexibility is controlled by highest order. Okay? Also, because we use the third order or fourth order or higher order terms, definitely it is much easier to be distorted by outliers. Even though such disadvantage, polynomial regression is still a good solution to model nonlinear relations. Okay, then let's move to a bit different approach, regression with step functions. The basic idea is breaking the whole region of x. Let's say this is the whole region of x from minus infinity to infinity. Breaking this x into several bins or intervals. Let's say first C, using some cut point. The cut point is the dividing point C1, C2, and blah blah CK. It actually divides in separate the region less than C1 and between C1 and C2, blah blah blah, like this, and larger than CK. Okay, then the basic idea is feed each bins with a constant value of y. So like this. Okay. For example, the observed x is between -1 and 1. We cut this range into two bins, like from -1 to 0 and 0 to 1. Then feed all data point between -1 and 0 at certain level, like this, and feed all data point from 0 to 1 with another flat value, like this. So this is our fitted line. Generally, for this approach, we first create cut point or nodes C1, C2, Ck in the range of x and construct step basis functions. Here, I is an indicator function. So we can actually make the C0 like I and indicator function of I for x is less than C0, which means this I is 1 if this argument is true. So if x is less than C0, it is 1, otherwise it is 0. So it indicates like this function. Okay. How about this? C1x. C1x is only, it is 1 only if this x is between C1 and C2. Then it shows like this function. So these are the all step functions. Okay. Here, note that for any k and l, ckx and clx, ckx times clx, this is actually 0 for any k and l, if k and l are different. Okay. Also, C0 to ck, they actually cover all range of x. In such a case, we call this ck, these functions are basis function. In the regression of this step function, y is expressed as the linear combination of the basis step functions like this. So yi is beta 0 plus beta 1 of the C1 plus beta 2 plus C2 and blah blah blah, the beta k times ck and epsilon. Okay, here so the C1 and C2 and blah actually including 0. These ones are this C1 is 1 or 0. So actually the height is determined by this beta 1. Okay, okay, this is the one typical example. In this example case, for this each data point is observed data. So in this case, we actually make the two cut point here and here. Then you make the three bins, this part and this part and this part. So each of the bins are modeled by fitted by flat line like this, and like this. And this whole thing is our fitted line. This is our estimation of f(x). Okay. So you may think this regression with the step function is quite stupid, right? Because it is too much simple. While it seems to be too much simple to be used for the real application, actually it is surprisingly used for many purposes. Mainly because this method is very interpretable. For example, when salaries over age is reported in a news article or other types of document, people like to use the salaries of 20s or 30s or and so on. But actually, these are the regression with the step functions, where step functions are between 20 to 29, because their salary is modeled by the one level, okay? And next bin is 30 to 39, and another flat value, and so on. So you can find such a case in from many other examples. The issue of this regression is mainly from the cut points. First issue is how many cut points we're gonna have. The number of cut points is actually for flexibility controls. But more cut points means more flexibility. Extremely, if we use the n cut points for n samples, we can perfectly fit this given training data. However, definitely it is overfitting. While definitely this number of cut points is a tuning parameter. However, conventionally, people like to use 3 or 5 cut points usually mainly because the use of the main usage of this one is for interpretability. If we have many cut points or many bins, even though it's more than 10 cut points, it is already too many for human beings to interpret the data. Then the next issue is, okay, so then where is the cut point, the location of the cut point? There is no definite answer, but there is a convention that people usually follow. Usually, cut points locate at each quantile point. For example, if we use 3 cut points, they are usually at the 25% quantile, 50%, and 75% quantile, which means at this quantile point, less than 25% of the samples are here. Okay, in total, if we have 100 samples along the x, from the smallest one to the largest one, if we just align as an order, so first 25 samples should be located on less than 25% of the quantile. Then next 25 samples gonna between 25 and the 50% point, and similarly 25 and 25. That is actually this 25, 50%, and 75% quantile means. If we want to use the 4 points, that should be 20, 40, 60, and 80. In total, 5 bins. Okay. Okay, so for this session, I'm gonna stop here, and in the next session, I will keep my discussion. Okay, thank you very much.